All right, go ahead.
All right, well, thank you for the introduction. So can you hear me okay and see my screen? Yeah, okay. And I'm keeping an eye on the time. So this is generally like 40 minutes or something. So definitely feel free to just interrupt me and ask questions. Like, it's gonna be pretty informal. So yeah, my name is Darryl Seligman. I graduated from Yale, where I worked with Greg Laughlin this last year. And I just started remotely postdoc at the University of Chicago. But what I want to talk to you about today is this object called Oumuamua, which was the first interstellar object that was detected passing through the inner solar system. And I spent a decent amount of time during my time at Yale in the last couple of years working on this body. It was pretty interesting. And so I want to go through some of the story about why this object was so interesting and what we think could be going on with it. So let's see, there we go. To get started, the story starts back a few years ago now, back in 2017. This is the minor planet circular that announced Oumuamua's discovery. And what you can see in the fine, it doesn't look that interesting if you just look at it, but if the fine print, it says the orbit below has an eccentricity of 1.2, which means that this object may be the first clear case of an interstellar comet. And that would be a big deal because it was the first one of this kind detected passing through the inner solar system. So if we just look at what was actually observed about Oumuamua, I know there's been a lot of speculation about what it was, but these are the photometric data that was taken of the object. So this is on the y-axis, the magnitude, and on the x-axis is just time. So it was only observable for a span of a couple of weeks. And we can see immediately one thing that you can get from this light curve is that Oumuamua's brightness variations change from bright to dim. You could see these, can you see my mouse actually?
Yeah, I can see it.
You can see it. So the brightness variations went from bright to dim every kind of 4 hours. And this is a log scale. So this was changing by a factor of 12 on average, from bright to dim. And so this was basically interpreted that Oumuamua was an elongated object that was tumbling, because an elongated body, when reflecting light, if it has a uniform albedo, will give you edge-on versus head-on projections that are very bright and very dim. But to get a factor of 12 difference in the brightness variations, you would need an elongation or an aspect ratio that was of order 6:1. And so 6:1 is much more dramatic than anything we've ever seen in the solar system. So this immediately was flagged as a reason why Oumuamua was strange. One of the most mysterious properties about Oumuamua was this extreme 6:1 aspect ratio. Now, this is the orbit of Oumuamua. So these are the inner solar system planets, and this is Oumuamua's eccentricity 1.2 hyperbolic trajectory. And another weird thing about Oumuamua was that it had no cometary tail. So generally solar system comets, what you'll see these beautiful cometary tails like the one that Neowise that was visible to the naked eye in the last couple of months. What you're seeing is there's ice in the comet that when it gets close to the sun heats up and sublimates. And what you're seeing is micron-sized dust particles that's trapped in that outflow. But Oumuamua had no cometary tail. So what that meant was that it either was not outgassing anything, or if it was outgassing, there was a lack of micron-sized dust particles to reflect sunlight. But this trajectory, it turned out, it was announced very shockingly that there was a 30 sigma significant detection that Oumuamua had a non-gravitational acceleration in its trajectory. So that means that its astrometric positions could not have been fit by a single Keplerian orbit under the influence of the sun. And so the best fit for the data was a force that was continually pushing Oumuamua away from the sun. And the magnitude of this force was about 1/1000 of the solar gravitational acceleration. So this is a not unprecedentedly strong non-gravitational acceleration, but a strong one. And generally, comets, when they outgas, will produce non-gravitational acceleration. So if you have an outflow from a comet where ice is producing a tail and an outflow, that will push the comet away from the sun. So this was interpreted that Oumuamua must have been outgassing, but there was no coma, which maybe you could get away with by just saying, well, it was outgassing, but there wasn't much small dust in the coma. But there's another weird and seemingly first order inconsistency between the interpretation that Oumuamua's non-gravitational acceleration was caused by outgassing and the light curve. So if you look at this light curve, the shocking kind of dramatic feature are these brightness fluctuations that change from bright to dim by a factor of 12. So remember, that's how we got the 6:1 aspect ratio. But there's another feature. So if you see these brightness variations are corresponding to tumbling the rotational period, these rotational periods are not changing. So over many tumbling times, Oumuamua has not spun up or spun down. It's actually going from bright to dim every 4 hours. So what that means is that the reason that this could be a first order inconsistency with the outgassing interpretation of the non-gravitational acceleration is that generally, if you just kind of naively imagine a jet exploding off of a body that's elongated, so something that's not spherical, then a jet that's strong enough to change Oumuamua's linear momentum or change the position of its trajectory by the amount that was observed should also change the angular momentum and spin it up or down. So I'll just actually go to the beginning of this movie. But what you're seeing here, this is a rendition of Oumuamua. This is not quite 6:1, but an elongated object. And what this blue line is showing is this is the position of a jet on the surface. So if the body is elongated, if the body is elongated and the jet comes off, explodes at a point on the surface that is anywhere but along one of these principal components, let me play that again, it will spin up very rapidly. And you would have seen that in the light curve, but clearly this body was not spinning up or down. So this seemed to be a complete first order inconsistency in the interpretation that Oumuamua was outgassing, and that's what led to the non-gravitational acceleration. So what we wanted to do in this paper, this was an AppJ letter I wrote with Greg Laughlin and Konstantin Batygin back in 2019, but we wanted to see, could you, if you had a more physically motivated outgassing model, and you took into account that physically motivated outgassing model with the spin dynamics of the body, would the spin period, the not changing spin period, be okay? So this is a picture of the comet 67P, which this is actually a spacecraft picture by something that got in situ measurements. And the sun is to the right. So you're seeing the coma of 67P. And basically, you could see basically what's happening, that volatile species are sublimating and moving out at roughly in the direction of the sun, and you're seeing dust that's reflecting sunlight. So what we wanted to do was analogously for Oumuamua, if you place the sun again to the right, if the jet is placed at the substellar point, which is the place of maximal sunlight, and the jet always explodes at the substellar point, what happens? So you can kind of imagine the rigid body dynamics. The jet explodes at the substellar point. That will then push Oumuamua away from the sun and also spin it. But then the position of the substellar point and the subsequent jet of sublimating material will move. So it turns out that in 2 dimensions, you can quite naturally explain such a system with a 1 degree of freedom Hamiltonian. And I don't want to get into the details of the derivation of the Hamiltonian, but I do want to talk about the interpretation of it. So for those of you it's been a while when you've done Hamiltonian dynamics, a Hamiltonian is just a statement of the conservation of total energy in the system. And what you have are kind of actions and angles or coordinates and momenta, conjugate momenta. And so in this Hamiltonian, the important thing is that this theta, little theta, is the jet venting angle, or the angle that the Oumuamua makes to the sun. So this is where on the surface the jet is going to explode. And the jet venting angle also tells you the orientation of Oumuamua with respect to the sun. And now big theta is the spin. It's the conjugate momenta to little theta, but it's also the spin about the z-axis, or the angular momentum. And frequency, omega 0 is a frequency, which depends on the strength of the non-gravitational acceleration and the size. And epsilon is just your aspect ratio, or the size, the B to A, the size of the long axis to the short axis. And now what you can do is take this Hamiltonian and apply Hamilton's equations, and what you get is a equation of motion for the small angle theta. Did my internet cut out there? Is everyone still following? Can you see that?
No, it's great.
It's good? Okay, great. So this equation, this is a second order nonlinear differential equation for theta. But the point is that this equation is very similar to the pendulum equation. So the pendulum equation, if you got rid of this term and got rid of this, the pendulum equation is just d squared theta dt squared is sine theta. And so what you can do to kind of quantify that, down here, what I'm showing is a phase space diagram, which on the x-axis, you have little theta, which shows the jet orientation, or the position of the jet along the surface. And big theta is just the spin, or the angular momentum. And these black curves here, these black lines correspond to level sets of the Hamiltonian, which just means for different constant amounts of energy in the system, Oumuamua will just stay on one of these level sets. So you have a separatrix here where inside of this, Oumuamua will just have librations, or back and forth pendulum-like oscillations, and outside of which you have full circulations. And I've color-coded the background here corresponds to the period of those oscillations. And now, I don't know if what people here think, but for me, it's kind of hard to visualize what's going on for a system in phase space. So I also animated the system, the exactly analogous system on this level set, but in real space. So what you're seeing on the right here, corresponding to this level set of the Hamiltonian, is Oumuamua rocking back and forth, where now the jet is shown in this blue line is perfectly tracking the substellar point. So the sun in this depiction is positioned behind us. And us as an observer on Earth, that was actually the physical setup of the problem, because we detected Oumuamua as it was leaving. So the sun was behind the Earth, which was behind Oumuamua. And so what this means, you can quite clearly see that Oumuamua will just rock back and forth like a pendulum. And the point is that this period does not change very much in phase space. And it doesn't change at all if you're on a level set. So what that means is that even under the action of a jet, which is able to spin Oumuamua up and down, the spin period will not change. So that if this is correct, that means that that 4-hour periodicity is consistent with the non-gravitational acceleration being outgassing. And now some of you might be wondering, so there's something weird about this, because I said that a Hamiltonian system is a statement of the conservation of total energy in the system. But you also have a jet, which is dissipating energy, or seemingly to dissipate energy. So that might seem inconsistent. And the reason that this works, it's actually quite beautiful. The jet, because the jet is able to track perfectly the substellar point, the jet is acting like a conservative force. And it is directly analogous to a conservative gravitational potential. So it's kind of like tidal forces on the moon, for example. But in the pendulum analogy, the analogy is direct, because the jet is acting like this force of gravity on a pendulum. So here at the pole, that's like holding the pendulum up at maximum potential energy. And as it spins through the minimum potential energy here, when it's swinging down, that's like when the pendulum reaches full kinetic energy and minimal potential energy. So what this means then, with this pendulum analogy, something that's quite elegant about this is that the pendulum has 3 kind of parameters that set the system, define the system. You have the length of the pendulum, the period of the oscillations, and the strength of gravity. And if you know 2 of those, then that sets the third. But for Oumuamua, we have measured the period we have measured the spin period from the photometric variations. And we also measured the strength of the non-gravitational acceleration astrometrically and independently. So what that then gives you, based on the equation for the frequency, is a purely dynamical constraint on the size of Oumuamua, if this is correct. And that size ends up being about 100 meters, which is exactly what you would calculate, which other authors calculated, if you just said, take the brightness that Oumuamua was observed at, assume an albedo for a solar system-like body, then how big of a body would you need to have? And that was also about 100 meters. So the real question is, if you have a realistic, like we know that Oumuamua was tumbling in 3 dimensions and that it was exhibiting non-principal component tumbling. So the question is, once you go to 3 dimensions and you introduce non-principal component rotation, can Oumuamua still, does that 1 degree of freedom Hamiltonian, then does the properties of the 1 degree of freedom problem translate to 3 degrees of freedom? And so without going through the details of what we did, without going through the details of how we did it, I did full rigid body, solid body dynamical simulations where you basically allow the full 3-dimensional body to move under the influence of the jet that tracks the substellar point, but now you're allowing for the full 3 degrees of freedom. So you're allowing it to tumble in 3 dimensions and the jet to move in 3 dimensions. And what we're showing here are the results of those simulations for 3 different fiducial geometries of Oumuamua. So you have a kind of 9-to-4-to-1 shape. You have a very thin cigar-like shape here. And here you have the pancake-like geometry. So all of them have roughly the aspect ratios that would be required to give you those factors of 12 and brightness variations. And the point is that it turns out that under long timescale dynamical simulations that we did, that Oumuamua never spun up. So what we're showing here, this is the kind of first 4 days when we had very high cadence data on Oumuamua. This is the real data, and these are the 3 synthetic light curves we made from these models corresponding to the 3 different geometries. And the point is that qualitatively, you got kind of the 2 features that we needed to reproduce. So you have the factor of 12 brightness variations in the light curve, but also you have, these are resulting powers periodograms, and you have that 4-hour spin period in all of them. So the point is that even under the 3-dimensional tumbling motion with a jet, which is continuously changing Oumuamua's angular momentum, Oumuamua never spun up. And so what that means is that, oh, and I should also mention that we did a lot of, I won't go through the details, but we did a lot of numerical experiments where we put stuff like varying albedos on the surface, and we put time delays and stochastic forcing on the position of the jet to make it more like a realistic comet. And that never resulted in significant spin up. So what that means is that the outgassing interpretation for the non-gravitational acceleration is not only consistent with the 4-hour spin period, but that tells you a dynamical constraint on how big the body was. So that was what made me think, because that dynamical constraint was so consistent with what you would get if you assume just from the brightness how big it was. That's why I really thought that this was correct. But the story was not over at this point, because the question of the composition of Oumuamua still remained. So in this paper, we said that the jet was composed of pure H2O, because, kind of right before this paper came out, there was a surprising announcement that there was a very significant non-detection of Oumuamua with the Spitzer Space Telescope. So that's looking in the near infrared. And what that tells you is that there were very stringent limits on the number of CO2, basically carbon-based molecules that were being sublimated, because Spitzer would have detected CO2 or CO. So there were stringent limits on the number of CO and CO2 particles that could have been in the outflow. So in this paper, we basically just said it was probably pure H2O or something like that. But it turns out that besides from the Spitzer, so now I'm going to transition to talking to the AppJ letter that was published a few months ago that's with me and my old advisor, Greg Laughlin. So there is besides from the Spitzer non-detection of Oumuamua, there is another constraint on the composition. And this one is a purely energy-based constraint. And the way this works, I'm just gonna kind of visualize, just to back up a minute and visualize what's going on. So we know where Oumuamua was very precisely from its orbit and its astrometric positions. And because of that, you know exactly how far away from the sun it was. And so Oumuamua is receiving energy in the form of solar radiation. And we are hypothesizing that this energy is going into sublimating icy volatile material, producing an outflow, and then pushing Oumuamua away from the sun. And so you can kind of formulate that by saying that the number of particles in that outflow, well, the energy balance is going to tell you that the number of particles is set by the energy from the sun, and then minus the energy that gets re-radiated in the form of blackbody radiation. And this energy, there are two energy sinks that the energy has to go into to provide the non-gravitational acceleration. So the first is you have to put energy into the latent heat of sublimation, which means that you need to put energy into the ice to break apart bonds between molecules to basically, that doesn't change the temperature of the individual molecules at all. It just makes them go from ice to gas. And then you have to put energy into kinetic energy for each of these molecules and speed them up to the sound speed in order to produce the jet or the outflow. And without going through the details of how we did it, incorporating the full three-dimensional geometry, this table basically is the punchline to our paper. But what we're saying is 4 different volatile species, based on the amount of energy that was received from the sun, that energy had to go into producing enough particles and speeding them up to the sound speed to account for the change in linear momentum that was observed. So basically what we're saying is this F is telling you what fraction of the surface that's illuminated needs to be actively sublimating in order to account for the energy budget that goes into pushing Oumuamua away from the sun. So we have several different volatile species here in this column. This tells you the temperature at which these species are going to sublimate. This is the bulk density in the solid phase. And then this is the latent heat of sublimation, or how much energy it takes to take ice and turn that ice into a gas. And then F is what I said, the fraction of the surface that needs to be actively venting or covered in the species. And it turns out that this energy constraint is remarkably severe. So almost nothing works. And something like H2O or CO2 just energetically could not. This is basically saying that something like H2O, Oumuamua did not receive enough energy from the sun for H2O to power the non-gravitational acceleration that was observed. And really the only viable species on this list that works is molecular hydrogen or molecular nitrogen. Now, I'm happy to discuss this more in the kind of questions period after this. But from now on, let's just say that it's molecular hydrogen and not molecular nitrogen. And the main reason that I'll give now, and I can give others later if we want to discuss it, is this. So molecular hydrogen, you only need 6% of the surface to be covered in hydrogen for this to work. Whereas for nitrogen, you would need 70% of the surface to be covered, at least. So that means that if it was nitrogen that was powering the jet, you would need to have a pristine nitrogen iceberg. But for hydrogen, you only need a little bit of the surface. So it's much easier to build something that's not pristine. So that's the main reason that I'll give for believing that Oumuamua is composed of solid hydrogen, not nitrogen. And so from now on, if you assume that Oumuamua was a solid hydrogen iceberg, solid hydrogen is a weird thing. And the reason it's weird, and you probably never thought of it before, is that, or I certainly had never thought of it before we figured this out, is that it sublimates at 6 Kelvin. So even though molecular hydrogen is the most common element in the universe, it sublimates at 6 Kelvin, so it's never in the solid phase. It's always seen in the gas phase. So I went back and was looking at just previous papers, if anyone had even written anything about solid hydrogen before, and there are a few papers written about solid hydrogen. One extremely intriguing paper posited this is back in 1996, posited that could baryonic dark matter be solid hydrogen? So the question Stephen White was trying to answer was, could the dark matter halo that the Milky Way galaxy lives in, could that just be all solid hydrogen icebergs that, you know, would never be detected? And he talks about the formation of these solid hydrogen icebergs in cold, dark, dense clouds. Unfortunately, I guess this paper hasn't gotten many citations, but the reason probably it wasn't very popular was because in the paper, it clearly doesn't work because you need a huge number of material locked up in solid hydrogen to actually affect the galactic dynamics of the rotation curves of the Milky Way. But just to see one Oumuamua in the last few years when Pan-STARRS, which is the operational facility in Hawaii that detected Oumuamua, was observational, is about 10 to the 11 orders of magnitude easier than affecting the galactic rotation curves. So the fact that Pan-STARRS detected one Oumuamua over the course of about 10 years implies that there's about 10 to the 26 of such objects in the galaxy, which is actually not, it's a huge number, but that's about an Earth mass of material per star. So that's a very reasonable amount of solid hydrogen or body. That's a very reasonable mass budget for Oumuamua-like objects in the galaxy. Now, at this point on, before we talk about the formation of these solid hydrogen icebergs, I want to try to convince you that the solid hydrogen is correct by showing that if you posit that Oumuamua was composed of solid hydrogen, or a good fraction of it was composed of solid hydrogen, then that explains every mysterious property about Oumuamua. Remember, we had the non-gravitational acceleration, the constant spin period, that's explained by the spin dynamics, and the energetic constraint is explained with the molecular hydrogen for the outflow. Then another weird property of Oumuamua was the very elongated shape, the 6:1 aspect ratio. And now I'm going to try to convince you that if Oumuamua came through the solar system and was kind of ablating hydrogen off the surface, that naturally produces an elongated body. The way this is going to work is that, remember, Oumuamua was tumbling and it's spinning. We know its rotation period is 4 hours. So 4 hours is much quicker than the timescale it takes for Oumuamua to significantly change its position in its trajectory and change the amount of flux it receives from the sun. So if you sit in Oumuamua's body frame and are rotating with it, effectively averaged over several spin cycles, what you see is an isotropic photon bath. So Oumuamua just sees photons isotropically hitting the surface. And what do these photons do? The photons basically come and hit the surface, and averaged over several cycles, they will isotropically remove hydrogen off of the surface. So what you can do is mimic that process and say, when you detect Oumuamua, you can take, you know, its trajectory, so you can backtrace it through its evolution through the solar system and pack mass back in the form of solid hydrogen back on in thin ellipsoidal shells to recover the shape that it had when it entered the solar system. So the way this is going to work is that at any point in its orbit, you pack on a thin ellipsoidal shell. You know what the mass of this ellipsoidal shell needs to be, which is basically this equation. What this is telling you is the mass of hydrogen that needs to be sublimated is set by the magnitude of the non-gravitational acceleration that was observed at that point. And that also corresponds to a differential volume shell, which corresponds to a thin ellipsoidal shell that you pack back on. And what I'm showing here, this is the result of that simulation. So it's a little counterintuitive, I admit. Basically, the reason I wanted to show it going forward in time, but really the way we do this simulation is you start here when Oumuamua gets detected, and you backtrace it. Angela, I think I might have had a glitch there. Is my internet still okay?
It's still working. The movie looks great.
Okay, great. So you take Oumuamua when it's observed, that's 6:1 in aspect ratio, okay? And what you do is backtrace it through its trajectory and pack mass back onto the surface. That's how the dynamical simulation works. And what I'm showing now here on the x-axis is time, and this movie is basically showing you the results of that simulation through time, through its orbit. So this on the left is roughly when you enter the solar system. A time of 0 is when you're at closest approach to the sun, and around here is when you get detected, okay? And these three plots, this is the total mass. So the mass is decreasing. That makes sense because you're ablating, you're removing hydrogen off the surface. The density is increasing. That makes sense because you're removing hydrogen, which is very low density. So what's left is the high density stuff. And also your aspect ratio is dramatically increasing. So when it's detected at 6:1, that could easily be explained by something that was 2:1 in aspect ratio when it enters the solar system. And this process is then shown on the right. What I'm showing is a scaled down version of Oumuamua, but the scales are correct. So the aspect ratio are correct. So when it entered the solar system, this is kind of live. It's quite feasibly, a reasonable looking object. But after this continuous ablation, you're seeing this wither away fragment. And this is directly analogous to what happens to a bar of soap. So when you use a bar of soap, you start with something that's, not spherical, but roughly spherical. And what you do is you kind of isotropically ablate soap or take soap off of the surface. The reason this process works, what ends up happening to the bar of soap is you get a smaller but thin sliver at the end. And that's what happened to Oumuamua, because if you're isotropically removing hydrogen from something here, if you take the same amount, if you imagine that you take a delta H off of the surface and the same delta H from the long and the small axis, delta H is always a larger percentage of the short axis than the long axis. So that implies this is like a runaway instability, where if you take the same amount off, you will always produce a dramatically higher aspect ratio body. And this is just showing, so this comes with the caveat that this simulation has some assumptions baked into it. So you have to assume, for example, what the bulk density of Oumuamua was when it was detected. And you have to assume what the albedo was. So what I'm showing here is the results of a few different simulations with different assumptions. And this is the aspect ratio again, the mass and the density. But the point is not to say, exactly what Oumuamua looked like when it entered the solar system. The point is to say that whatever you assume about the body within reasonable assumptions, Oumuamua has a more moderate aspect ratio when it entered the solar system than when we detected it. So that explains, whatever you assume about it, that still explains why it was so elongated. It's just because it was the last withered away fragment after this continuous ablation. And in reality, what's happening is we actually backtrace this through the galaxy as well. So as it travels through the galaxy, instead of solar photons, it's getting exposed to cosmic rays and high energy photons from stars. So you can backtrace this as far as you want in the galaxy to rebuild Oumuamua's shape when it was formed. So what this plot is showing, this is just the trajectory of Oumuamua in the context of the outer solar system and the inner solar system. And these are just showing you what Oumuamua looked like for two different observers at location 1 when it's entering, then when it gets detected, and then when it exits. So you can naturally see that Oumuamua just goes from something that's moderately reasonable looking to this kind of thin fragment at the end. Now, so I think I hope that I've convinced you now that this, if you just assume that it's a hydrogen iceberg, it would explain the non-gravitational acceleration, the spin dynamics, and the shape of Oumuamua. So the first thing I want to discuss is just the formation of hydrogen ice. So where could you form something like this in the galaxy? Because remember, hydrogen ice sublimates at 6 Kelvin. So you need to go to colder than 6 Kelvin to freeze out hydrogen. So that's basically telling you that this has nothing to do with planet formation, that Oumuamua could not be a disk product, because there's basically nowhere except for maybe the very furthest reaches of protoplanetary disks where you can freeze out hydrogen. So the only place in the galaxy where it's feasible that conditions can reach almost the cosmic microwave background temperatures and densities high enough for hydrogen to freeze out onto dust grains are the starless cores of the giant molecular clouds. So the idea, and we could talk about the formation of these more in the question and answer period too, is that in the starless cores, which are very cold, the idea is that some of these starless cores, not all of them have to do it, only a small fraction need to do it, but some of these starless cores cool to almost a CMB temperature, where hydrogen can start to freeze out onto dust grains. These dust grains kind of coagulate together and eventually build snowballs, and you get centimeter-sized snowballs, which then gravitate by the force of gravity, come together, and you can, in the lifetime of a starless core, build very large hydrogen icebergs. Now, if you now buy that, what's kind of amazing about this idea is that if you assume that Oumuamua was born in a prestellar core, then that explains the last and subtlest and most mysterious property of Oumuamua, which I have not mentioned yet, because it's kind of subtle. But the weirdest thing about Oumuamua by far was the trajectory it had as it was entering the solar system. So Oumuamua was clearly on a hyperbolic trajectory, and its incoming velocity, or velocity at infinity, was about 26 kilometers per second. So that sounds very fast, but that is also basically exactly what the sun is doing. That's basically exactly consistent with the sun's peculiar velocity with respect to the local standard of rest. So what that means is that with respect to how all the stars move in the galaxy around the sun, Oumuamua was sitting almost exactly still, and we intercepted it. But we know from galactic dynamics that as tracer particles in the galaxy age, they get dynamically heated, actually predominantly from scattering off of giant molecular clouds. So older stars have higher dispersions. And Oumuamua's incoming trajectory was so shockingly close to the local standard of rest that it really can't be much older than 45 million years. And that should immediately tell you that Oumuamua can't be a disk product, because if you eject something from a protoplanetary disk, then the ejection process is actually very, it's not violent at all. It's just gently ejected. And that ejected product will have the exact same kinematics as the star that it came from. But the giant molecular clouds are very young. They don't last very long. So the idea is that the dispersion of the giant molecular clouds in the galaxy is very, very low. So if you form in a starless core at a GMC, the core goes away in a very short amount of time. And what's left, basically the icebergs that form in the starless core are they're not even ejected at all. They just sit there. The core dissipates because it fails to produce a star. And the icebergs are just left on the same orbit that the GMC had. So if it was formed in a starless core, then this would also explain the weirdest thing about Oumuamua, which is the fact that it was basically said that it's so shockingly young. I just want to check the time. I want to leave time for questions, but I just want to mention that there was, this year there was a second interstellar object that was detected. This is Borisov. This is Hubble images that Dave Jewett took of it. And Borisov is quite clearly an interstellar comet. So, I mean, that should be obvious because there is a clear coma here. Won't go into the details of this plot because I want to save some time, but basically Michelle Bannister is leading this observational campaign we have with MUSE on Borisov. And what we've shown is basically that we're basically using MUSE, which is an integral field unit, to look at the composition of the coma of Borisov. And what we're finding is that the composition of Borisov basically makes it look exactly like typical solar system comets. So Borisov, in all of the ways that Oumuamua was weird and mysterious, Borisov is acting exactly the opposite. And it is quite clearly a typical comet, but an interstellar comet that was ejected from a protoplanetary disk. And so I think what this is telling me is that Borisov and Oumuamua are two separate, distinct populations of interstellar objects. Borisov being the clear comets, icy comets that are ejected from the far reaches of these protoplanetary disks, probably by extrasolar Neptune-like analogs. And Oumuamua-like objects are hydrogen icebergs that are dark and have no comas that are formed in the starless cores of the giant molecular clouds. And I guess I just want to end by mentioning that in my 2018 paper with Greg, we showed that it would be very possible energetically, it's very feasible to send an interception mission to an interstellar object. So using Oumuamua as a test case, we showed that it would be shockingly easy to send a rocket from Earth that would have intercepted Oumuamua. And the reason that this is because Oumuamua came close to the Earth. So because it comes pretty close, this needed a delta V of something like 4 kilometers per second to do. And so what we then showed is that the Vera Rubin Observatory is going to detect many, many more of these objects. And it'll be very feasible with wait times of only a couple of years to detect one that you could feasibly send an interception mission to. And it's quite clear that something like a mission like this, there is now the Comet Interceptor mission, which has been selected by ESA but it's quite clear that in the near term or mediocre term, moderate future, something like an in-situ observation might be possible. And I want to end by mentioning that barring the opportunity to do an in-situ measurement, one way to test the hydrogen iceberg hypothesis is, I'm just going to go here. One way to test the hydrogen iceberg hypothesis, if you remember this plot, actually, yeah, this was the plot I was looking for. This aspect ratio evolution, the most dramatic aspect ratio evolution happened right around periastron. So, I've only showed a couple of months here, but these lines are asymptotic. So what I showed in the 2018 paper via Monte Carlo simulations is that Very Observatory will detect future interstellar objects like Oumuamua. If they look exactly like Oumuamua, they will detect them with such an unprecedented change in sensitivity. You will detect them before periastron. And so feasibly, if this is correct, you should be able to watch it live, change shape. Because remember, we got the aspect ratio from the brightness variation. So if this is right, one prediction is that when these things come through and you detect them before periastron, you'll be able to see the brightness variations get more dramatic over time. So I guess I can keep sharing my screen, but I'm gonna stop and take questions. Thank you very much.
That was really great. We usually just if anyone just wants to unmute themselves and ask a question.
Should I keep my screen shared or?
Whatever you think.
Sure.
So I might have a question.
Yeah, could you speak closer to your microphone? Or maybe I can just turn you up. I think I can hear you now, I think.
Okay, so thank you for this great talk.
Thank you.
I'm not sure I understood something about like the Oumaumua becoming more and more like having a higher aspect ratio over time. Just you saying that you are losing isotropically mass from Oumaumua, but I got from your picture of the pendulum or whatever that you spend much more time being lighted by the sun at the tip of the ellipse than at the center of the ellipse. Do you take into account that or?
Okay, that's an excellent question. So the answer is yes and no. So, okay, let's see. So I did all of this work and I did take all of that into account because I basically extended the Hamiltonian I did to, this is great because I have tons of backup slides, but I extended the analysis I did to include basically that point jet model. Once I realized a lot of the surface, if it's a lot of the surface is covered in the ice, it should, the other extreme is a surface that's completely covered. So then I extended the Hamiltonian formalism to include jets that covered the entire illuminated surface. So at each point in time in the Hamiltonian, you have to integrate jets, do a contour integral along the entire surface. So I did all of that and got this nasty Hamiltonian, which is much more complicated, and it's exactly the same in phase space. So taking that into account doesn't really change the constant spin period. And then moreover, in reality, the situation is, as you rightly mentioned, is between this because of both the surface covering fraction is more like 6%. So it's probably more like the point jet thing, maybe. And then, as you said here, in the very idealized two-dimensional case, it spends more time here. So I did take that into account. Basically, what I was doing was with the full surface covering jet Hamiltonian, doing the semi-analytic model, but instead of assuming constant, basically integrating over the entire time that it spends at different parts to get the change in X and Y. And that basically didn't make any difference. And I had another point I was going to make. But yeah, I guess the point is just that, yes, I looked into account and I was trying to do very complicated modeling to do the shape correctly. And it was such a small difference to you can look at the paper for what we actually did, but it's very simple what we do. And just basically the assumption that it's isotropic, but that assumption is fine. And then another reason not to go too in depth down this rabbit hole of the assumption of how you do the shape modeling is like, I mean, this doesn't sound good, but there are way worse assumptions in what I did than that. So that assumption is pretty fine. Assumption that is not, you know, there's no reason to think this, that we observed Oumuamua from there until basically there. And that was when you, basically the non-gravitational acceleration, the magnitude is 1/1000th of the solar gravitational acceleration, but it falls off like 1/r². That's the best fit. But to do this whole model, we just assumed that was the strength of the force throughout the entire trajectory. So that is a much worse approximation than the semi-analytic model for the shape that we did. I think it's fine, given that Oumuamua is gone, we don't know anything more, and it must have been outgassing the entire time. Like, I think that's a fine assumption in the context of trying to say, you know, we're not trying to say what the aspect ratio was when it entered or the specifics about it. We're just trying to say the aspect ratio was more moderate.
Mm.
Does that answer your question?
Yeah. Okay, thanks.
There was a question in the chat. Would the change in mass and aspect ratio throughout its solar system journey affect the light curve or non-gravitational acceleration predictions? Or was our observation window too small?
So who was asking this question?
Tyler McMacken. He's still here. If you want to unmute yourself, Tyler, you can.
So let me just make sure I understand correctly. Was the change in mass and was the change in mass from the hydrogen ablation, would that have changed the non-gravitational acceleration or the light curve during the time it was observed? I think that's the question. You can speak up if that's not right. Basically, the issue is that no, because unfortunately, we only observed Oumuamua for like 2 weeks. It was so dim. We caught it. We were lucky to catch it, but we caught it when it was like 40 lunar distances away and it was already leaving. And then it disappeared because it's so dim, it disappeared here. So, I mean, I could say no, but you can quantify that, right? Like I don't have it. I didn't have it here, but there's also the size, but the aspect ratio is what you'd be interested in, but it barely changes. Not enough to notice in the light curve over the time that we were observing it. But that is, and also the total amount of mass that would have changed is not, yeah, I mean, it's not enough to significantly change the amount of the non-gravitational acceleration that was observed over 2 weeks. But that is both a valid question and something that we should look out for if we see one prior to periastron in the future.
Anne-Marie, you had a question?
Anne-Marie.
Hey, great talk. Thank you. So I have the controversial question that you were probably waiting for. The director of the CFA disagrees with you. So Abu Loeb wrote a paper saying that molecular hydrogen iceberg, let me lower my hand here, wouldn't survive the journey unless it had originated very close to the solar system. So I've seen a lot of what Abby's written, but I haven't heard your kind of comeback on it. Do you want to talk about that?
Yeah, sure, I can talk about that. So Avi's paper is, yeah, so I'll just, for people who aren't familiar, so Avi basically 2 weeks after our paper came out, wrote this paper that said, the reasons that he disagrees with this interpretation is, one, he doesn't think hydrogen icebergs can form in the molecular clouds. And then if Oumuamua came from the closest molecular cloud or a close giant molecular cloud, which is quite far away, I forget the exact distance, in the time it would have taken to travel from there to us, the cosmic microwave background, I mean basically like the energetic particles in the galaxy would have destroyed the entire iceberg by the time it got to us. So it doesn't live in the galaxy because the cosmic rays will do the same thing over longer timescales that the solar photons do. So we did in this, so I didn't show it, but we did in the paper, we talked pretty extensively about we also backtrace the simulations through the galactic trajectory. So we showed that they live for up to about 50 million years, maybe 100 million years, depending on what you assume and how big they start out with the cosmic microwave, with the, sorry, it's been a long day, but with the high energy particles hitting them. The thing is that, so there's this paper that Tim Hallett wrote. If you look at what you can do is, so yes, so you cannot trace Oumuamua back to a host system because there's two reasons. One reason is because, you know, the galaxy is chaotic, but the main reason is actually we don't know the dynamic, even with Gaia, you don't know the dynamics of the star, the phase space information, the velocity and the position of the stars well enough to backtrace 50 million years and actually get an exact home system. But what you do know is what you could say is what association of stars Oumuamua is similar to. So Tim Hallett's paper basically shows like Oumuamua is definitely part of the Carina or Columba moving groups. Like without it, like if Oumuamua was a star with that velocity, it would be associated with one of those things. So Oumuamua didn't form in that far away cloud. Oumuamua formed with Carina or Columba. And it's just moving with them, and then we're there. So we are moving through a high flux area of these things.
But would they have to have formed, would Oumuamua have to have formed a really long time ago because it wasn't
No.
this information?
So what Tim shows in his paper, you basically backtrace Oumuamua's trajectory, a lot of different simulations of it because it's only a statistical thing you can do, but basically shows it was there in the same region that Carina and Columba were forming they were forming like 45 million years ago. So It was there and it formed, it's like 45 million years, it's perfect. So Avi's paper actually works very nicely with that paper. There is in terms of the like passage through the galaxy, that's actually fine. A point that he raises that's very valid is, you know, the nucleation of hydrogen. So the nucleation of hydrogen onto dust grains in a giant molecular cloud core. So he's right that probably the smallest micron-sized grains, it's not going to work because just from a kind of like, if you assume that it's an inelastic collision or like an inelastic collision, then there's enough latent heat to re-sublimate the hydrogen. But so I'm actually not part of this paper, but Greg and a current student of his has a paper that's being submitted very soon, which shows that you can easily, like, for about 50 micron sized grains, you can easily build up big icebergs. And it works even better than how we described it in the paper. It actually works very nicely. So you could stay tuned for the new stuff that Greg is coming out with.
Thanks.
Does that answer both points of obvious?
Oh yeah, yeah, it does.
I had a response ready.
Can I ask, you just kind of mentioned that extrasolar Neptune analogs are throwing comets at us.
Yeah, I didn't explain that at all.
Can you just like a 2-line like?
I can do better than that. So this is pretty. Tell me I have a backup slide. Yeah, I do. So this is actually why I was originally interested in Oumuamua, because before I thought it was a hydrogen iceberg, I thought basically when in my first paper, I thought it was an interstellar comet that just had some like regolith on it that protected it from being from sublimating and being like a comet. And that's why we proposed doing an interception mission so you could see that stuff. And the reason that's super interesting is because if you assume, so basically the way it works is like in the solar system, you have giant planets like Jupiter, Neptune. What happened was while they were forming, if you agree with the Nice model, which you can agree with or not, but if you agree with the Nice model, basically the giant planets underwent a dynamical instability and like moved around a bunch, went unstable, and Jupiter and Neptune basically scattered a bunch of stuff from this primordial planetesimal disk, scattered a bunch of stuff and created the Oort cloud. So what happens is it's basically just a gravity assist. So Jupiter, something comes close within to the hemisphere of Jupiter, and then Jupiter can just move it enough so that it comes out with a larger velocity. And then what happens is you take a kind of close-in primordial disk, you scatter these things out to being only very loosely bound, and that's how the Oort cloud gets created. But then the galactic tidal potential in passing stars will then eject a lot of, like 90% of that material into interstellar space. And so Oumuamua's detection implies the fact that we're so bad at detecting Oumuamuas means that there's like one in the inner solar system at any given time, which means that there's like 10,000, I think it's something like 10,000 inside of Neptune, which means that there's 10 to the 26 in the galaxy. And if you say roughly that's about an Earth mass of material per star, which is roughly what we ejected. So what that's telling you is that there, oh, and I should say that Jupiter, like for a planet to scatter something out, like the reason Earth doesn't do it is the Safronov number has to be greater than 1. So what that means is that the planet has to be massive enough and far enough away from its star such that the escape velocity from the planet is greater than the orbital velocity. So it's like you can give it enough energy to eject it. So Jupiter and Neptune are the ones that can do that. And the reason it's the so this is amazing, but basically, so we know now from like, we roughly know from radial velocity measurements that Jupiters are like pretty rare, like a 10% thing. But I imagine people saw those D-sharp images of the protoplanetary disks. Those basically what those show, those gaps and rings are like 50% ubiquitous. So if those gaps and rings, one of those papers basically show those gaps and rings, if they are like, maybe they're not planets in there, maybe it's like an MHD thing, but like if they are planets, those are Neptune analogs based on their spacing. So what it means is that like every other star has a Neptune. And then if you say every other star has a Neptune, that means that every star is producing a bunch of Oumuamua-like things. Those numbers to order of magnitude give you the exact same number. So and then that just works for Borisov because Borisov was further away but easier to see. So it's roughly the same amount. So an amazing corollary is just that this is confirming that those, I mean, not completely confirming, but it's very, very circumstantial evidence that those gaps or rings are actually Neptunes and that Neptune analogs are like a 50% occurrence thing.
That's really cool. I want to see like a whole nother talk on that. Do you have a paper?
I don't have a paper, but I think Milena Rice has a paper about that.
Cool. Is there any other questions? Well.
Yeah, I guess. Oh, sorry. Go ahead.
No, go ahead.
Yeah. So just to clarify? So the 6%, you said 6% of the surface was molecular hydrogen. Like, should I think of Oumuamua as being like, what's the rest of the composition? Do you have a sense of that, or like, is that unconstrained?
So I guess Oumuamua is like a little red. So the reflectance spectrum showed that it was like moderately red. That's kind of consistent with molecular hydrogen. I guess, so the short answer is I have no idea, but like if you form in the giant molecular in a prestellar core, right, then the way it works is that as the core cools, you basically differentially freeze out different molecules. So once you get to hydrogen, everything else is frozen out. So you can pretty much, I think it's very safe to assume there will be other stuff that comes onto the iceberg as well. So we literally do this for extrasolar planets all the time. Like a very good assumption is that the hydrogen iceberg just has the bulk composition of the core in terms of metallicity. So there's probably, it probably has some metallicity fraction. And then, as it was forming, it probably nucleated other dust particles as well. So I think that's a fine assumption. I'll also say that it doesn't, so the 6% is a lower limit, right? So a lot of people had when this paper first came out, a lot of people had the objection. It was like 6%, it's not that much hydrogen, like that can't be right. Like the 6% is the reason we like this because it's a lower limit. It doesn't have to be pristine, but it could have more. There's a lot of assumptions into our modeling, right? So it doesn't have to be 6%. And another interesting point is that, maybe it formed with a lot more hydrogen. Maybe it formed with a surface. So when it's in the prestellar core, like the prestellar core is pretty self-shielded. So you're not being exposed to much of the cosmic rays. So it's not being ablated. But as it if it travels through the solar, if it really came from Carina or Columba, then it travels through the galaxy for like 45 million years. It is going to be zapped by cosmic rays, and that takes away the hydrogen, but not the other stuff. So the surface could have a lot of the remnant stuff that wasn't taken away from the hydrogen by the time we saw it. So it's very possible, or even just from the solar encounter. So it's very possible that a lot of that had a lot higher surface covering fraction previously, and you've just got the remnant left over. And that, by the way, that argument also extends the lifetime of these objects. So there's another cute prediction is that there should be two populations of hydrogen icebergs, the young ones, which will have a lot of hydrogen on the surface, and the very old ones, which are just the stuff that gets left over. Does that answer your question?
Yeah, thanks for the clarification.
Okay.
All right, it's 1:40, so I'm gonna stop